Hey guys, this is Professor Janacek, and I want to go over an example where we integrate using partial fraction decomposition. So let's take a look here. We have the integral of 5x squared minus 3x plus 2 over x cubed minus 2x squared dx. So first, let us just work with that fraction. We have 5x squared minus 3x plus 2 over x cubed minus 2x squared. First thing we need to do is factor that denominator. I notice that I can factor out an x squared. And I think that's about all we can do with that. So now if I look at setting up my partial fractions, I'm going to go ahead and treat x squared as a linear factor that has been repeated. So I'm going to treat it as an x, but it has been repeated, so I'll need to write it as a squared term as well. And then x minus 2 is the other denominator. Just so you know, I could have instead written it as x squared plus x minus 2 as the two factors. So in this case, though, I've got all linear factors. Again, this is a linear factor repeated, but I'm still going to think of it as a linear factor, which means my numerators, 1 degree lower than that, they're all constants. But they're all potentially different constants, so I'll name them 3 different things, A, B, and C. By the way, if we were using a squared factor, then I would have used ax plus b, a linear factor for its numerator. Of course, the last one is always going to be linear. So notice I could have approached it using these two, a squared factor and a linear factor. You would end up with the exact same result however you went about it. Either way is completely acceptable. All right, so moving on. The next thing we need to do is to go ahead and combine these fractions. So the common denominator is, again, x squared times x minus 2. The first one has an a. To build up, it'll need an x and an x minus 2. The second one has a b. In order to build up to the common denominator, it needs an x minus 2. The third one has a c, and in order to build up to the common denominator, it simply needs an x squared. So if we combine these, if we add these, we get a times x minus 2 plus b times x minus 2 plus cx squared. All of that is over our common denominator. Now we know that our original fraction is equal to this fraction we have here, this rational expression that we have here at the end. I also know that these denominators are the same, right? In fact, I could even see it here. Those denominators are the same, which means the numerators must also be equal. So we can go there and just write that bit down. Now, again, you could also write this as an equation and clear the fraction. You can think of it either way, but I know that those numerators must be equal. So 5x squared minus 3x plus 2 must equal ax times x minus 2 plus b times x minus 2 plus cx squared. Now we'll go ahead and distribute. On the right-hand side, multiply things out. We get ax squared minus 2ax plus bx minus 2b plus cx squared. The next thing we'll do is to go ahead and combine all of the like terms. I have an ax squared and a cx squared. So that means a plus c is the coefficient for x squared. We have a negative 2ax and a bx, so we can combine those. That gives us negative 2a plus b for the coefficient of x. Again, notice I kept that negative inside here and a positive on the outside of that group. Don't want to get anything don't want to lose those negatives. And finally, the only constant we have is negative 2b. So that's going to be here at the end. All right, the next step is that since we know these are equal, then I know that the coefficients of x squared must be equal to 5, the coefficients of x must be equal to negative 3, and the constant must be equal to 2. So we can set up a system of equations that a plus c must be equal to 5, negative 2a plus b must be equal to negative 3, and finally, negative 2b must be equal to 2. To solve this system, well, let's see, that's pretty easy. This last one gives me that b is equal to negative 1. Using that in this middle equation, we can solve for that and get a is positive 1. And now using that in our first equation gives us that c is equal to 4. Thus, we can now go back to our integral. We know that this is equal to a over x plus b over x squared plus c over x minus 2, and I now know what to use for a, b, and c. So we get the integral of a over x plus b over x squared plus c over x minus 2. There's the integrand. Now we can go ahead and integrate each one of these independently. All right, so the first one actually, that's going to be pretty easy to integrate. Hopefully we know that one. The second one, I'll go ahead and factor out that negative 1. And you know what? Looking at that, I'm probably going to go ahead and consider this as x to the negative 2 for that integrand. The last one, let's see, I'll go ahead and factor out the 4, but I'll leave this one in this form. And I think we are ready to integrate. The integral of 1 over x dx, that's simply the natural log of the absolute value of x. And then I've got minus the integral of x to the negative 2 dx. If we integrate that one, we end up with plus x to the negative 1 plus 4 times the integral of 1 over x minus 2. For this one, we will do a little bit of a u substitution. We'll let u equal to x minus 2, then du is simply dx, and we are integrating 1 over u du, which is the natural log of u. So that gives us the natural log of the absolute value of u, but u is x minus 2. Of course, don't forget we have that arbitrary constant on each one of those. Collected it all, put it in there in the back as plus c. All right, a few things we can do to clean this up a bit. Let me go ahead and write x to the negative 1 as 1 over x. And I'm also going to put these natural logs together. I do notice that the 4, using my properties of exponents, I can write as property of logarithms, I can write that as an exponent. Also notice because it's an even exponent, I don't need to write those absolute values anymore. The other thing I can see about this is, again, those properties of logarithms. If I'm adding two logarithms with the same base, it turns out I can multiply their arguments. So I've got the natural log of the absolute value of x times x minus 2 to the 4th. Of course, plus c there in the back. And there you go. We have integrated this, making it much easier to integrate by decomposing the fraction. There you go. Enjoy!